Okay, this is my last video for Unit 10. In this video, we're going to talk about hybridization, and we're also going to talk about something called sigma and pi bonds. All right. Now, some of the stuff that I'm going to be talking about in this video is more than what you need to know. But I think that it's important to understand how this really occurs. All right. So hybridization. In a molecule, in a covalent compound, when atoms bond together, what ends up happening is the orbitals where they have valence electrons, which for the most part are going to be your s and p orbitals. There are some, exceptions that actually use some of their d orbitals to bond, but for the most part, we're using s and p orbitals. So what ends up happening is those orbitals mix together. So they kind of like get mixed up in like a blender, and they make these hybrid orbitals that have new energy and shape that are suitable for bonding. All right. So I'm going to go through. We're only going to talk about tetrahedral, trigonal, planar, and linear, and me showing you the diagrams. And the reason I'm doing that is because those three, if we look back at our chart for Vesper, those three, tetrahedral, trigonal, planar, and linear families, those three are like sp3, sp2, and sp, respectively, hybridization. So trying to draw like a d orbital is way too complex, and I'm not even worrying about that. So let's look at this. If we wanted to create 4 areas of electron density, that would be a tetrahedral molecule, right? In the tetrahedral family. So we're not even talking about lone pairs and stuff like that. We still have 4 areas of electron density around a central atom. We need 4 orbitals. So think about the valence electrons. And I understand that on your page, the copying, like some of the things are a little bit harder to see, but hopefully on here it's a little bit easier. So to use 4 orbitals, we're going to use 1 s orbital and 3 p orbitals. And here it's kind of hard to see, but we have a p orbital that's along the y-axis, a p orbital that's along the z-axis, and one that's along the x-axis. So again, it's a 2-dimensional drawing representing something 3-dimensional. It's kind of hard to tell, but yeah, that's what's going on. So we need that 1 s and those 3 p's. So these all get mixed together, and we end up creating 4 sp3 hybridized orbitals. So we have 1 s and 3 p's. If we mix them all up, and we make 4 equal orbitals, 25% of it's going to be s, and 75% of it's going to be a p character. Okay. Now, in order to make those 4 sp3 hybridized orbitals, or when we make them, they're going to evenly distribute themselves around the central atom, making 4, actually I don't even know why I'm outlining that, making 4 sp3 hybrid orbitals. And those sp3 hybrid orbitals, the optimal bond angle is 109.5 degrees. That's where we get that bond angle from. So that's the hybridization. That's why it's sp3. You just need to know that it is sp3. That anything with 4 areas around the central atom, whether those areas be bond pairs or lone pairs, 4 areas, the hybridization is sp3. This is the why behind it. Okay. Let's look if we wanted to make 3 areas around a central atom. 3 areas would be trigonal, planar. So in order to make 3 areas, we need 3 orbitals. So we're going to use 1 s and 2 p orbitals. This other p orbital that we're not going to use is going to be unused. It's still there though. It doesn't disappear. It's just unused. All right. So only the s and the 2 p's get mixed together, and they make 3 sp2 hybridized orbitals, and then again we have this one leftover p orbital that was unchanged. It didn't get mixed together. So what I have in white here are my 3 sp2 hybrid orbitals. And then I have my leftover p orbital that was unused. And it's just kind of there in the background. It's not going to be used for bonding. For the most part, it will when we talk about sigma and pi. All right, so that's going to just kind of backburner that for right now. But looking at those 3 sp2 hybridized orbitals, that bond angle is 100 and, I don't know how to write apparently, it's 120 degrees. 3 things around a central point, most optimal angle is going to be 120. So the sp2s are my hybridized orbitals and my leftover p. And the third one I'm going to look at is if I'm making 2 areas around my central atom. That's going to be a linear molecule. So 2 areas means I need 2 orbitals. I'm going to use an s and a p. I'm going to have 2 p orbitals that are unused. But my s and p are going to hybridize into my 2 sp orbitals. And then here are my 2 unchanged p orbitals. So looking on the diagram up here, the white orbitals are my sp hybridized orbitals. Notice that that bond angle is 180 degrees. And then my 2 unused p orbitals are just kind of chilling there. Not really doing much right now. I'll shade those in orange and green. All right, but those are my 2 unused or unhybridized p orbitals. Right? I'm not going to do 25. I'm not going to do those examples. We can do that in class. But I want to jump to sigma and pi bonds, where we're going to talk about what in the world, like, so how do these things actually bond? All right? How do these things actually bond together? So let's skip here. All right. Let's start off with the top. Sigma bond. A sigma bond. It's not a 6. It's a sigma. It's another Greek letter. It's a lowercase sigma. You've probably seen a capital sigma before. It looks like this. Yeah, when you're finding the sum of things. The lowercase sigma looks like a weird 6. All right. Erase that. I don't need that capital sigma. All right. So a sigma bond. What happens in a sigma bond is it's when we have a head-to-head or head-on overlap of orbitals. All bonding occurs when orbitals are overlapping. Bonding between 2 different atoms happens when you have an overlap, but it depends on the type of overlap that's going to tell you if it's a sigma or a pi. All right, and this part that I'm going into is the background. It's the why behind it. You don't need to know the why. You need to know the what, but I feel that the why helps you know the what. Okay, so all bonding has head-to-head overlap or head-on overlap. So imagine you have 2 s orbitals overlapping, or you have an sp3 hybridized. What happened to my p? You have an sp3 hybridized orbital overlapping with an sp2 hybridized orbital. Whatever. You have some sort of overlap. Okay? There is free rotation about this. All right? And it's a head-on or head-to-head overlap. Like I said, all bonding, no matter if it's a single bond, a double bond, or a triple bond, all of those have one sigma bond. Pi bonds only occur in double and triple bonds. These, we're going to use the empty p orbitals, those empty p orbitals that were unused in sp2 and sp3 hybridization. All right, remember we had those unused p orbitals. This is where we're going to have a sideways overlap. And this drawing, this is where the drawing gets a little bit difficult. So let me show. We have 2 empty p orbitals. What ends up happening is they sideways overlap and share space. where the electrons can move among them. So it kind of looks like this. And I know that looks really weird, but that is a pi bond. All right, and you've seen pi before because you've all taken a math class. All right, but this here, this portion here, is the important thing. Learn this. A single bond consists of one sigma bond. A double bond consists of a sigma and a pi. A triple bond consists of a sigma and 2 pi's. The next part of my video, I'm going to go more into the why. I'm going to draw the actual overlapping of all of these orbitals. I feel that it is important to look at these things. You will never have to draw these beyond what you draw maybe for this video. If you don't draw it, I'm not going to fault you for it, but I do want you to watch this, okay? I do want you to just watch and pay attention. And then the last 2 pages of our Unit 10 packets, page 22 and page 23, that's going to be more of the types of questions you're going to see with this, okay? Let me go through. This is actually what I'm going to be drawing. These drawings suck, though. All right. Ethane, C2H6, C2H6. We've got 2 carbons, and we have 6 hydrogens. Each carbon is sp3 hybridized. Because let me actually draw out the quick Lewis structure of this. Each carbon has 4 areas of electron density around it. Each carbon is bonded to 4 things. So each carbon is sp3 hybridized. So that means that each carbon is going to have 4 sp3 hybrid orbitals coming off of it. And I suck at drawing these, but they're all sp3. They're supposed to be kind of like teardrop shape, but they're all sp3. And then this carbon has 4 sp3s coming off of it as well. And these angles aren't 90 like I'm drawing here. They're really 109.5. Just trying to draw something 3-dimensional on a 2-dimensional medium is difficult. And then we have my 6 hydrogens. Each hydrogen isn't, none of the hydrogens are hybridized. Only the central atom gets hybridized, okay? Only things that are bonded to multiple components get hybridized, all right? So all of these hydrogens only have an s orbital involved in bonding, because each hydrogen only had 1 valence electron, and that valence electron is living in the 1s orbital. Now all of these overlaps are head-to-head overlap. All of these are sigma bonds. All of this was head-to-head overlap. It's all sigma bonds. No pi bonds. Pi bonds only occur when you have sp2 and sp hybridized orbitals. Okay? So we have, if we count up the number of head-to-head overlaps, we have 1, 2, 3, 4, 5, 6, 7. 7 sigma bonds. And that's sigma. Okay? But you could also figure that out by the fact that we have 7 single bonds in the Lewis structure. So you will be able to figure out the sigma and pi based off of just the Lewis structure. I'm showing you the overlap because I feel that it is important for the background information. Okay? But ethane, if you draw the Lewis structure, you count up the number of single bonds, those are all sigma. Now let's throw in a double bond. Ethene. We already drew this before, but it looks like this. All right, so we've got 2 carbons. Both of those carbons they have 3 areas of electron density around them. So both of those carbons are sp2 hybridized. So those carbons have 3 sp2 orbitals surrounding it, sp2 hybridized orbitals. And they are going to be at a bond angle of 120. And that's easier to draw on paper because that bond angle is like flat. It's not 3-dimensional. sp2, what happened to my p? There we go. And then we've got my 4 hydrogens. Just like before, hydrogen is not going to hybridize. It's just going to utilize its s orbital. Now, on those carbons, these are sp2 hybridized. Let me go back to this. And there we go. Oop, too far. In an sp2 hybridization, when the central atom does sp2 hybridizing, we have an unused p orbital. That p orbital is still there. That's my unused p orbital. And remember, when my unused p orbitals are there, they end up doing sideways overlapping. So we end up getting this sideways overlap, which is from my unused p orbitals, well, sideways overlap. So all of these sections where like the S and the sp2, they are, oh, my phone's ringing randomly. I'm going to ignore that. My sister's calling me. Doesn't she know I'm at work right now? All right, so what was I saying? The s orbital from hydrogen and the sp2, they're head-to-head overlap. Same thing with the 2 sp2 orbitals within the carbons. That's a head-to-head overlap. But then the sideways overlap, that's the sideways overlap. So that's going to be my pi bond. And here, sigma, 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 sigma. That's why a double bond is a sigma and a pi, because we have a head-to-head and a sideways. So in this, we have 1, 2, 3, 4, 5 sigmas and 1 pi. All right, and we also can figure that out based off of the Lewis structure. Last one. And then we'll do examples more like what you're going to see. Ethine, C2H2. This looks like this. Both of those carbons have only 2 things attached to it, 2 areas of electron density around each carbon. So each carbon is sp hybridized. So carbon and carbon. sp hybridized means we're going to have 180 degrees between my 2 sp orbitals. We've got my hydrogens attached to that. Head-to-head overlap with my s orbital and my hydrogen, from my hydrogen. And then, let me go back. Here we go. When we have sp hybridization, we have 2 unused p orbitals. So we're going to have 2 sections of sideways overlap. So I'm going to draw one set of p orbitals in one color, and they're going to sideways overlap. I'll draw that in a moment. And my other one I'll do in green. That's contrast enough. This is kind of going like in and out of the board. Again, it's kind of hard to see 3-dimensional like this, but that's kind of what it's going to look like. So let me draw the overlap of the ones I drew in pink. Oops, pen. There we go. So sideways overlap here. And then for my green, sideways overlap here. So that's why it's better to watch me as I draw this, because looking back, you're like, what in the world's going on? But if you see me as I draw this, if you actually watch the video as I'm drawing this, it makes a little bit more sense. So each of these head-to-head overlaps is going to be a sigma bond. So we have 1, 2, 3 sigmas. And then each of the sideways overlap is going to be a pi bond. Pi, pi. So we have 2 pi. And again, you could have figured that out based off of just the Lewis structure, because each single bond is just a sigma. A triple bond is 1 sigma and 2 pi. Right? And the reason why is what I drew here on this screen. Okay? So now let's look at a few examples of what you're actually going to see. All right, so let's look at this one. We have glycine, which is one of the simplest amino acids. We actually need to finish the Lewis structure here. We have to put in lone pairs to make everything happy. Nitrogen, remember, nitrogen likes to have 3 bonds and 1 lone pair. Oxygen likes to have 2 and 2, so each of my oxygens is going to need 2 lone pairs. All right, so what are the approximate bond angles about each of the 2 carbon atoms, and what are the hybridization of the orbitals on each of them? So I'm going to number my carbon atoms. It doesn't really matter which one I number 1 and which one I number 2. When we do our organic unit, it will, but for right now, I don't care. So we're going to say this is carbon 1 and this is carbon 2. So carbon 1, it has 4 things attached to it. So it's a tetrahedral molecule. So the bond angle would be 109.5 degrees. Since there's 4 things attached, it's going to be sp3 hybridized. And this is just going to come from memorization. And if you learn the reason why, it's less memorization and more learning it, but for your purposes, if you just memorize, it's fine. Okay? For carbon 2, that carbon has 1, 2, 3 things around it. So its bond angle is 120. And because there's only 3 things, it needs to use 3 orbitals, so it's going to be sp2 hybridized. All right, then we have our 2 oxygens and the nitrogen. We're kind of doing the same thing for the 2 oxygens and the nitrogen. So my 2 oxygens, oxygen will also hybridize. Hydrogen is really one of the only things that doesn't hybridize. So oxygen, as long as it makes at least 2 bonds, it's going to hybridize. So we've got oxygen number 1 and oxygen number 2. And I don't need to number the nitrogen because there's only 1 of them. So for oxygen 1, there are 3 areas of electron density around that oxygen. We've got the bond, the double bond, and then the 2 lone pairs. So that oxygen is going through sp2 hybridization because 3 things around it means you make an sp2 hybridization. Oxygen number 2 has 1, 2, 3, 4 areas of electron density around it, which makes it sp3. And then the nitrogen, we're going to do the hybridization and the bond angle. Well, it has 1, 2, 3, 4 areas around it, so it's sp3 hybridized, and its bond angle is 109.5, or right around 109.5. Actually, because there's that lone pair, it's a little less than 109.5. Now, to count up the number of sigma and pi, remember, for every single bond, you're going to count a sigma. 1, 2, 3, 4, 5, 6, 7, 8. For a double bond, you're going to count a sigma. So we now have 9 sigmas. And then a double bond also is a pi. So 9 sigma and 1 pi. The way I would count this is I would actually count 1, 2, 3, 4, 5, 6, 7, 8, 9 sigmas because I know that double bond is a sigma. And then because it was a double, it's also going to be a pi. If there was a triple, it'd be 2 pi's. Let's do one more. So this one, we're missing lone pairs on the oxygen. And I couldn't find a better or a better drawing of this one on the internet. So it's a little fuzzy. But looking at this one. So we're going to indicate the hybridization and bond angle about each of the central, quote-unquote, central atoms in the molecule shown below. My central atoms are going to be carbon, 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 and nitrogen. So let's number my carbons. And then we have the nitrogen. So we have carbon 1, carbon 2, carbon 3, and nitrogen. And even though the question doesn't ask this, we're also going to determine the number of sigma and pi bonds. So carbon 1, there is 1, 2, 3, 4 things around it. That's sp3 hybridized. Its bond angle is 109.5. Carbon 2, there are 1, 2, 3 things around it, so that's sp2. That bond angle would be 120. Carbon 3 has 1, 2, 3, 4 things around it, so it's sp3 hybridized with a bond angle of 109.5. And then that nitrogen has 1, 2, 3, 4 lone pairs count as an area of electron density. 4 things around it, that's sp3. That bond angle makes it a little less than 109.5 degrees. And again, even though didn't ask, let's count the number of sigma and pi. So for sigma and pi. Sigma, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And we only have one multiple bond, one double or triple. And we have one double, so that's a single pi. Sorry, single as in a 1 pi bond. Okay? So that's how you do that. So there'll be more practice like this in homework 10A, but that's it for Unit 10. You've now completed this unit.